The 11,000 object surge. The Vera Rubin Observatory just identified 11,000 new asteroids in a single test run before its primary mission even officially began. This is not just a high-speed search for space rocks. As of May 2026, the launch of the Alert Production Pipeline has turned the southern sky into a real-time data stream, generating 800,000 alerts in its first full night of operation. This massive volume of raw evidence is doing more than cataloging the solar system. It is providing the first concrete proof that our long-standing models of the dark universe may be structurally flawed. The sheer throughput of the Smoothness survey telescope is outstripping our theoretical ability to process what we see. This data deluge starts at the heart of the world's largest camera, engineering the ultimate sky movie. Mapping the dark universe requires more than a big mirror. It requires a 3.2 gigapixel camera capable of capturing the entire southern sky every 3 nights. This creates a high-definition time-lapse of the cosmos. Think of it as moving from still photography to a high-frame-rate digital film of the universe. By processing 20 terabytes of data every night, Rubin is identifying every flicker, move, and explosion across billions of light-years. This engineering feat allows us to see how gravity bends light across the entire sky simultaneously. But the distribution of that gravity, which we attribute to dark matter, is showing up in places where the simulations say it should not exist. This spatial mismatch is the first signal that our dark matter math is broken. The dark matter smoothness crisis. Standard cosmology predicts that dark matter should clump into dense, jagged knots over billions of years. However, the early science data from Rubin describes a universe that is surprisingly smooth. If dark matter were the cold, slow-moving particle we have spent 40 years looking for, the gravitational lensing maps should be far more chaotic. Instead, the 2026 alerts show a diffused distribution of mass. This suggests that dark matter might not be cold at all, but rather a warm particle with its own internal pressure. This discrepancy is not a minor error. It is a fundamental conflict between the Big Bang's starting conditions and the physical reality Rubin is recording right now. This smoothness problem forces a total rewrite of how we think the cosmic web is held together. The galaxy formation paradox. The Hubble and James Webb telescopes showed us massive galaxies appearing too early in cosmic history. But Rubin is now showing us the environment where those galaxies grew. We are finding far more ultra-diffuse dwarf galaxies than our models of dark matter halos can support. A counter-argument from the April 2026 COLIBRE simulations suggests that better modeling of gas and dust might save the standard model without needing new physics. However, Rubin is finding these ghost galaxies in such high numbers that the gas-only explanation is beginning to look like a desperate patch. We are seeing a mismatch between the number of dark matter buckets available and the number of galaxies actually sitting inside them. This is the missing satellite problem, but in reverse. The signal under the noise. The early data from the Rubin Observatory indicates that we are moving out of the era of cosmic discovery and into a period of fundamental debugging. By comparing the 800,000 nightly alerts to the smoothness crisis in dark matter distribution, we can conclude that our standard model was likely a useful approximation that fails under high-resolution scrutiny. For mission strategists and astronomers, this means the next decade will be defined by a search for a more complex dark matter particle that interacts with itself. The real implication is that the fundamental constants of our universe might not be constant at all, but local effects of a much larger physics we have yet to name. We have spent decades building the map. Now that Rubin has finally turned on the lights, we are realizing the terrain does not match the paper. Watch for the first cross-correlation results between Rubin and the Euclid Space Telescope this December to confirm if the standard model survives the year. Subscribe for more.